This video is on gases at standard conditions. So first we have this question here. How many moles of krypton are needed to fill a 1.5 liter container at STP? Well, we know from previous units and from our reference tables that standard temperature is 273 Kelvin, which is 0 degrees C, but it's more important to remember the Kelvin temperature since we are dealing with gases. And standard pressure is 1 atmosphere or 760 millimeters mercury or 101.3 kilopascals. So in saying STP, they are telling us that the temperature is 273 and the pressure is 1 atmosphere. They're also telling us the volume in this problem of 1.5 liters. And they're asking for how many moles. And moles are in. So this is a very classic PV equals nRT problem. PV equals nRT. We're going to solve for N. So we need to divide both sides by RT. So N equals PV over RT. And now it's just plug and chug. So my pressure is 1 atmosphere. My volume is 1.5 liters divided by R, which in this case, because I chose to use my pressure in atmospheres, I need to choose this value of R. Because it's the one that has atmospheres in it. And then our standard temperature is 273 Kelvin. All right. Kelvin cancels, atmospheres cancel, liters cancel. And the only thing not canceled out are moles. So N is going to be equal to 0.067 moles. Okay. So that is just kind of a review of the ideal gas law. Now, using this standard temperature and pressure that I have up here, I would like for you to do one and calculate the volume which 1 mole of gas occupies at STP. You can pause this video, work out that problem, and then I'll go over the answers. Okay, so in this particular problem, we have PV equals nRT. We're solving for V. So that means we're going to divide both sides by P. So V equals nRT over P. They told us that it is 1 mole of a gas. R, if I choose my pressure, just like I did before, as 1 atmosphere, R value is going to be 0.0821 liter atmosphere mole K. And then my temperature, standard temperature, 273 Kelvin, divided by standard pressure, which is 1 atmosphere. Atmospheres cancel, mole cancels, Kelvin cancels. All I'm left with are liters. And so my volume is 22.4 liters under standard conditions. Well, this is per mole. So this is actually going to end up being a really good conversion factor for us. For a mole of any gas, we have 22.4 liters. And so at STP, all gases have 22.4 liters per mole. That lets us know that there are 22.4 liters in 1 mole of any gas. And so we can use this as a conversion factor and a shortcut for the ideal gas law, as long as it's at STP. So this only works at standard temperature and pressure. So I'm going to go back to this problem that I have right here, where I used the ideal gas law to find the moles of krypton. I'm going to do this in another way since I know it's at STP and I know that the conversion factor that we just found is 22.4 liters per mole. So what I can do here is let me change pens, is I have 1.5 liters of krypton. And if I want to go to moles at STP, I can use this conversion factor. Liters are on top, so liters have to go on the bottom. 22.4 liters in a 1 mole of any gas. And 1.5 divided by 22.4 equals 0.6, 0.067 moles. I did not write that well. Let me try this. Notice that's exactly what I got plugging it into PV equals nRT. So this becomes a very handy shortcut, and it's one that we can remember because it is on our reference tables right here. Volume of 1 mole of any gas at STP is 22.4 liters. So we can use that as a shortcut to go from liters to moles or from moles to liters as long as the gas is at STP.